Okay, welcome back to another session of population ecology. Today we are going to be getting into population growth now. And specifically this session is going to be covering exponential growth curves, but we do just need to cover a few basics before we get into those curves. So, population growth. There are some variables that we need to consider to determine the growth or decline of a population. So we've got births, which would obviously increase the population, deaths, which will decrease the population. Now, there are two more variables that may not be quite as obvious right off the bat, and those are immigration, or arrivals from other populations through dispersal, and immigrations, meaning that we're losing individuals from this population because they are migrating to other populations. Alright, so this is the equation that we need to keep in mind for determining growth. So growth equals the births plus the immigration, minus the deaths plus the immigrations. And anything above 0 would indicate that that population is growing. And of course, the larger that number is, the faster it's going to be growing. Next up, if that equation ends up being less than 0, so a negative value, that means we have negative growth, which essentially means we've got a declining population. And again, the larger that negative value, the faster the population is declining. And there's a third one. If our equation equates exactly to 0, that means that our population is static. There's no growth or decline. All right, so the key thing to keep in mind here is that we're looking at growth curves. And this is because populations do not tend to grow linearly. We don't expect it to just be a straight line from a small population as it grows towards a large one. As a population grows, more individuals can contribute to the next generation. Essentially, as more individuals are born, population gets bigger, meaning that there are now more individuals to produce more offspring. So it's going to exponentially increase with each generation. And is this going to lead to overpopulation? Well, we need to keep in mind that there are finite resources in any environment. The Earth itself is finite. It's not infinite. There's only so much to go around, and this is regarding things such as food and also space as well. And this is going to bring into question carrying capacity and will lead us on to logistic growth curves, which is going to be next week's session. So this week we're going to be specifically covering exponential growth, but just kind of showing you where this sits in relation to other kinds of growth curves. So today, just exponential. So yeah, let's get into that, exponential growth. Now, often when I've seen this taught, it's kind of delivered in a way that's assuming that the learner already understands what exponential means and how it works. We're going to do a little bit more of a deep dive today into kind of the maths behind it that makes exponential growth take place. So there is going to be a little bit of numbers to wrap your head around, but I'm going to try to take it nice and slowly for you. And yeah, let's get into it. So exponential growth, we're going to have a bit of a table here that's tracking the generations and the population size. So this is going to extend downwards once we've wrapped our heads around the first row. So right at the very beginning, the first generation of a population, we're just going to assume that we're starting with a population size of 2 individuals. And we've got here the next column here, we've got offspring per individual. So that's how many offspring these two individuals are going to produce each, and this is going to be on average. So this will be an average that we already know based on the species. So obviously different species are going to have different reproductive outputs. And this is offspring per individual, so per one of these. So what we need to do is we need to multiply these together. So 2 individuals times 2 offspring each, and that equals 4 total offspring. And now these 4 total offspring, they are in the next generation, aren't they? So that's going to bring us round to generation number 2. We have 4 individuals in generation 2. And again, these 4 individuals, on average, they're going to produce 2 offspring each. There's a little bit of inbreeding going on here, but we won't talk about that. So again, we're going to have 4 times 2 individuals each. We're going to have 8 offspring produced by the second generation. And of course, because they're produced by the second generation, they are by definition the third generation. So this is going to extend downwards now. We're going to add in the extra rows. So yeah, third generation, 8 individuals. And you can see that because each individual on average is producing 2 offspring each generation is doubling in size. 2, 4, 8, 16, 32, 64, and so on. And you can see that after just 15 generations, we have 32,000 individuals in that generation. So you can see that this gets out of hand very quickly. It starts off small and it remains rather small for a while, but then it begins to pick up very rapidly. And we can display this on a graph, and this is what it's going to look like. And this is what an exponential curve is, where it starts out kind of flat and then quickly ramps up and up and up. So yeah, exponential curve, that's one example for you here. Now, this is obviously the most simplest model here. We're only considering offspring output for our growth. However, there needs to be some more considerations here, because what about offspring survival? It's not very likely that every single offspring that is produced actually goes on to produce their own young or surviving into that next generation. So let's consider that we have an offspring survival of 75%. So only 75% of the offspring actually get to pass on their own genes and produce their own offspring. So we're going to add a new column here. We've got offspring survival. And because we're considering 75% survival, again, this is going to be on average for the species. We're going to take the total offspring. So these individuals are still producing 2 offspring each for a total of 4 total. But then only 75% of them survive, so we need to multiply by 0.75, and this equals 3. So in total, 3 offspring from generation 1 are going to move along to be generation 2. So there we go, I've got 3 producing 2 offspring each, that's going to be 6, so 3 times 2, 6 times 75% equals 5. Now this is being rounded up or down because obviously 75% of 6 isn't exactly 5, but of course we can't have a decimal point of an individual. It's going to be one or the other. So we've got 5 there. So we're going to have 5 starting generation 3 down here. You can see that continues down, and you can see that we've got a much smaller population size by generation 15 this time round. Just by being 75% less, we've changed from 32,000 individuals in the previous example all the way down to 584, which is a much smaller exponential growth, but it is still exponential. So we're going to just show that graph again, or a new graph demonstrating this growth, and you can see we've still got that exact same exponential curve. It's just at a different scale now, so only reaching up to around the 500 mark as opposed to reaching the 32,000 mark on the previous example. But you've still got exponential growth. All right, one thing to just notice here is that we are assuming 100% mortality with each generation. Or in other words, there's no overlap from one generation to the next. What I mean by that is that we've got 2 individuals in generation 1. They produce 3 offspring for generation 2, and we're assuming that the population size during generation 2 is only 3 individuals. So in other words, these 2 individuals here died before we counted the second generation's population. So this would be accurate for species that die after reproducing. For example, a lot of insect species, including mayflies, they don't live for very long in their adult form. They produce eggs and then they go and die, I think within like 48 hours or something. So for things like mayflies, this is still a pretty reliable model. And yeah, so how a population is modeled is extremely species specific. We're now going to move along to an example or a hypothetical example where we're trying to model a species where there is generational overlap, in which case determining the overall population size is going to be a little bit more complex than just the offspring output. So let's do that now. But first of all, we're just going to get rid of these 2 columns here because we don't really need them for our calculations anymore. So you know what's happening here, offspring per individual and total offspring. We're just going to remove these columns and just shift this along, just so we've got a little bit more space to do the next lot of math. So there we go, there's our reduced table here. Offspring survival is the key thing to be keeping in mind here. But we also need to keep in mind previous generation survival now as well. And additionally, we're changing population size here to generation size. So in generation 2, we've got 3 individuals in that generation, but we do need another column that's capturing any surviving individuals from the previous generation. So let's do that. But first of all, just keep in mind our survivorship curve from the previous video. Remember, we had type 1 species, type 2 species, and type 3 species. Now, we're going to assume that our species that we're tracking here is a type 1 species, meaning that a lot of the individuals survive through towards maximum lifespan. So we need to track these individuals that are surviving beyond their generation. And that's what we're going to put in this column here, previous or individuals from the previous generation that are still surviving. And then once we've got that, we can then add them up to work out the total population size. For this example, we're just going to focus on the timing for generation 8, just so we can just focus on the maths over here and not look at all of the numbers all at once, because that would be a little bit over the top, a little bit overwhelming. So for generation 8, we need to work out the previous or the individuals from these previous generations that are still alive. And based on being a type 1 species, we're going to assume that individuals from the very previous generation, from generation 7 in this case, 90% of those ones are still alive during generation 8. If we jump back 1 generation, we've got 75% from 2 generations prior are still alive. So we're getting a little bit further down the curve here. So that would be this part here. That's our second generation back, 75%. And then 3 generations back, only 30% of those 10 individuals are still surviving during generation 8. And again, 10% surviving of those 7 individuals, and above that we've got 0% surviving. So we're going to do a little bit of percentage math here. So we're going to convert the percentage to the number that is surviving. So 23 individuals, that means 21 are still alive during generation 8. And we've got 11 of the 15 still alive at this time here, 3 of the 10 surviving, 1 of the 7 surviving, and of course we've got 0 of any of these surviving. That's just too long ago. Those ones have all died of old age. So for generation 8, the previous generations or previous individuals surviving from those prior generations is going to be the sum of all of these values here. So let's add those up. 1 plus 3 plus 11 plus 21. And that adds up to 36 individuals. So we've got 36 individuals surviving from generations before generation 8. And we've got 34 within generation 8. So we're going to add these two values together. 34 plus 36 is 70. And of course, this is just going to be repeated for each of the other generations. And that fills out all of our numbers here. And there's our new true population total that is considering both the current generation, which would be the cohort that we learnt about in the previous video. So current generation plus surviving individuals from previous generations would equal the total population. And again, we can plot this out on a graph. And as you can see, we are still getting that exponential growth curve. All right, so let's just talk about some of the considerations that we need to think about when we are plotting population growth. So our example considered reproductive rate. We looked at each individual on average producing 2 individuals or 2 individual offspring. And then on top of that, we considered survival rate, which was 75% survival for first year offspring, and then also considering those survival rates of those prior generations, which was 90%, then 75%, then 30%, and then 10%, and then 0%. So those are our things that we have considered for our growth curves that we've looked at. However, we did fail to consider a few different factors here. So as we mentioned during the beginning of this video, we did not consider immigration or immigration, which could have some other implications on that growth. And additionally, we did not consider any subsequent broods of those surviving prior generations. So if I just jump back to that table, so we've got these previous surviving individuals from prior generations now, so this 36 from before generation 8. Are these ones here producing additional offspring as well on top of the 51 produced by this generation? So the 51 produced by generation 8, are these 36 from previous generations also producing their own offspring? We have not considered that, so that could also have more implications on our growth curve here. So yeah, very important to be aware of all of the factors that may impact population growth. And the final factor that we have not considered in our growth curves that we've looked at today is that there is a diminishing resource availability, which is what I was talking about near the beginning, about carrying capacity, the fact that environments are not infinite. As the population gets too large, there's going to be less resources to go around, which may reduce survivability or reproductive rate. And that's going to be the topic of the next session. Hopefully that has given you a bit of a deep dive into growth curves. And yeah, that's all for today. Make sure to subscribe if you want to get any of my following videos on this. There's a lot more to cover still. And yeah, hopefully you're enjoying, and I'll see you next time.